Okay, guys, let's do it. This is energy homework. This is the energy homework, the one you're working on in Quest this week. I'm going to go over a few problems and how to set them up, and this should get you kind of what you need. All right, let's look at number 1. I'm going to look at 1. I'm going to look at 3. Let's see, 4, because that goes over conservation of energy. And let's see, I'm going to go over 7. 7's a little bit... no, it's not really tricky, but I'll show you how to use like the kinetic energy equation. And then we'll look at number 9 and 19, because 19 is kind of challenging. Okay, so that should kind of get you what you need. All right, so let's go through it real quick. I'm going to show you how to do this stuff, and then we're going to break free, break loose, and kind of do everything. All right, so all these variables you should know. Like, these are not new variables at all. All right, so the first one, mass, right here. That's M. Let me use a different color. 5.9 meters, that's height, or distance in the y direction. This right here is G, right? How much potential energy? So that's question mark potential energy. And this is gravitational potential energy. We're not using any other type of energy right now. All right, so let's go ahead and do that work real quick. I'm going to move this out to the side. All right, so that's kind of nasty looking, but that's all right. Okay, so what equation, if we look through our equation sheet here, and you obviously have more equation sheets than I do, or you have more on your equation sheet because you get to use your homework and everything right now. But let me see real quick. Let me see right here. Just scroll this down a little bit. Not on the second page. Here we go. So we're going to be on the second page of our formula chart. Potential energy gravitational, or GPE, is right there. Here's the kinetic energy equation. Okay, so I'm going to move that out of the way. So let's see. So what was our... This is why we need to write it down instead, right? Because I can't even see anymore. All right. So gravitational potential energy equals M times G times H, and I have all 3 of those, so I don't need to move anything. The mass was 53.8, so I'd plug that in. Gravity 9.8, and height was 5.9, and you'll get the answer like that. Cool? All right, so that's how you would do that first problem. Okay, let's go on to the next one. Yeah, I said I was going to do 3 next, because 3 is a little freaky paziki. All right. Test rocket is fired vertically from Cape Canaveral, and the mass of that was 13.7. Fuel gives a kinetic energy of 2,200 joules. Remember that joules is the unit for energy. That's very important. It's also the unit for work, and that's going to matter next week. All right, the acceleration due to gravity, or the G, is going to be 9.8 again. And this one's asking for what was the height. So what is the change in height that it's going to have over that period of time? So this one, all right. So what equation do we have that has acceleration due to gravity, kinetic energy, and mass? Well, if we look at the equation chart, the equation sheet here, really nothing, right? We really don't have anything on there that matches that. But check this out. We really have the law of conservation of energy, where the kinetic energy initial and the potential energy initial has to equal the energy after. So this is kind of like that before and after collision thing we did last chapter with momentum. And that really comes from this, where the idea of the mechanical energy is basically kinetic plus potential energy totaled up together. And those were all those charts we were looking at that had bar graphs and things like that, whereas kinetic energy decreased, potential energy increased, because potential energy is related to height, right? Whereas the kinetic energy is related to how fast it's moving. And when does an object, if it's going in a parabola like this, when does an object have the greatest kinetic energy? Right at the beginning, when it's launching. As it goes up, it gains height, so its potential energy increases until it reaches the top of its apex, where it runs out of speed. The velocity is 0, but it's equal, this potential energy up here, this potential energy at the top, where it is highest, has to match the kinetic energy at the bottom when it took off. So even though this has a lot of speed at the beginning and no speed at the top, we know that the max or the energy at all times, the total mechanical energy, the KE plus the PE, has to be equal to the same ME, mechanical energy. And remember that mechanical energy just kind of means the total between kinetic and potential, right? So that idea, this idea of this green dot right here, having to be equal to the blue dot at the top. So this is kinetic energy max. This is potential energy max. These two have to be equal to each other because of the law of conservation of energy, and I'll show you another example of that in a little bit. Okay, so with that, check this out. This is kind of like when we did impulse momentum, where if you have impulse, you have momentum, that sort of thing, and you can set them equal to each other. All right, so watch what I'm going to get to do here. Since this is the equal to the max potential energy that you're going to have, guess what I can do? I can say that these two are equal to each other. So now guess what? Potential energy, this is my equation, is mgh. I'm looking for h. I always have g, and this time I have the mass. My potential energy is going to be equal to my kinetic energy in this case, because it's the top of the path. All right, so let's see. So I'm going to go ahead and move mg over here. So how do I get rid of m and g at the same time? You divide by mg, right? And you'd be done. Okay, and you just plug in the numbers and you're done. It's very important that you know how to plug stuff in this one, because you're not going to have mass in a lot of these problems, and you'll see that in a second. All right, let's move on to the next one. Okay, let's try 4. 4 is kind of a similar type of problem. So a bobsled slides down an ice track with 0 initial speed. So my V initial is 0. 198 meter hill, so the height is 198. Acceleration or gravity is 9.8. What is the speed at the bottom? So V final equals question mark. All right, now this one, guess what? What is happening in this situation when I draw this out? So up here, this is mechanical energy initial. And down here, this is part 1. This is my before. This is my after. My initial and my final down here. So this is my mechanical energy final. And what do I know about mechanical energy initial and mechanical energy final? These two have to be equal, right? So now I'm going to break this up into mechanical energy initial has to be equal to mechanical energy final. What makes up mechanical energy? We said it's the sum, and if you look in your vocab notes, of kinetic energy plus potential energy. This is initial. So guess what? It has to be equal to the kinetic energy plus the potential energy, use a different color, plus the potential energy final, right? All right, now let me ask you something. I know the equation for kinetic energy is 1/2 mv squared, potential energy is mgh, initial equals 1/2 mv squared. This looks like a lot of writing, but all I'm doing is expanding the equation, plus potential energy final. Okay, now watch this. What was my speed at the beginning? It was 0, right? So guess what happens? The 0 we get plugged into here. This all goes away, right? So you don't need to worry about that. At the bottom, though, what's my height? My height at the bottom, I messed up right here. Hold on. Oh, too much. This should be mgh. Sorry about that. My height at the bottom is 0, right? So this actually all goes away, right? So watch what's about to happen. Okay, so since that's all gone, I essentially have this. My potential energy at the beginning has to be equal to my kinetic energy at the end, right? So essentially all I'm doing is setting mgh initial to 1/2 mv squared final, right? And since I'm looking for the v final, I just do algebra. All I'm doing is algebra. So how do I get rid of this 1/2? Just like I did in every other chapter, multiply by 2. 2 mgh equals mv squared. How do I get rid of m? See, now watch this. You weren't given mass, right? You were not given mass. So you're like, how do I do this if I'm missing? I don't have that. I don't have that, and I don't have that. I'm missing a variable, so how am I going to be able to do this? Well, look, this is why I told you all year not to plug stuff in before you start doing work, because look what's about to happen. I'm going to divide by m, since it's the same object, and look what happens over here. Guess what? I never needed it. That's pretty cool, right? Okay, well, I think it's cool. Whatever. Okay, so now, essentially, this is what we got. I'm just going to rewrite this over here because I'm running out of space. 2gh equals v squared. And how do I get rid of a square? You're done, you plug in. All right, and you plug in and you get your answer. All right. All right. Let's see. And I think I'm just going to leave it at that for right now. I'll make another video for 9 and 19. Those are a little bit more challenging, but I think you can figure it out from here. Just real quick, though, just run through number 10. I just kind of want to show you that this is the other equation that you're using for it. Yeah, never mind. I guess I don't have 10 on here. But just you're identifying variables. Like if you end up with something that looks like this, like I have an m given. So my givens are m and v. Well, then what's my equation I'm using? If I'm trying to figure out my kinetic energy, then you would just use 1/2 mv squared. Okay, so that's not very hard, right? So just you're identifying your variables. You make sure it plugs into the right equation by looking at this guy right here. Yep, mass velocity. All right, good luck.